In this lecture, we will discuss about the quantum harmonic oscillator. In the previous lecture, we have already discussed about classical harmonic oscillator, and in this lecture, we are going to discuss about quantum harmonic oscillator. Now, we know that the potential energy of a harmonic oscillator V is equal to half k x square. What is k? K is the force constant, and V, that is potential energy, is a continuous function of the coordinate x, and therefore is completely different from systems we considered so far where the potential is constant over a region. So potential energy V depends on x, where x is the displacement of the oscillator. Now, as V is equal to half k x square, we can write that V is equal to half, and in place of k we are writing in this way because we know that omega is equal to root over of k by m. So from that constant, from that equation, we are writing the value of V is equal to half, and in place of k, so that is m omega square. So we are writing m omega square in place of k. So omega is equal to, we know that 2 pi nu, where nu 0 is the linear frequency, omega is the angular frequency. So half k x square, that can be written as half m omega square x square, where omega is equal to 2 pi nu. So omega square will be 4 pi nu 0 square. Nu 0 is the linear frequency, omega is the angular frequency. So potential energy V, that can be written as half m omega square x square. We have learned this when we have studied the problem of classical harmonic oscillator. Now we all know about the expression for Schrodinger equation. So if we put the value of the potential energy in Schrodinger equation, then the time independent Schrodinger equation will look like this, that is d square psi by dx square plus 2m by h cut square into E minus V, this is V, V is half m omega square x square into psi is equal to 0. This is time independent Schrodinger equation. Now we will define two parameters. The first parameter is y is equal to root over of m omega by h cut into x, and lambda is equal to 2e by h cut omega. Now y and lambda, they are dimensionless parameter. I will suggest you that please you practice on a notebook that whether the dimension of y and lambda, that are means those are dimensionless or not. You know the dimensional analysis. So from the dimensional analysis, if you perform, then you will see that y and lambda, they are dimensionless parameters. So after defining these parameters, and if we replace these parameters in equation 4.73, then this equation will be simplified. So let us put lambda is equal to 2e by h cut omega, and y is equal to m omega by h cut root over of m omega by h cut into x into this equation. So this equation will become, if we put these values here, so this equation will look like d square psi by dy square plus lambda minus y square into psi is equal to 0. You can check that 4.75 and 4.73, they are same equation. If we put the value of lambda and y defined here into equation 4.75, then you will again get the equation 4.73. So equation 4.75 has been obtained from equation 4.73 from these parameters. We have defined these parameters, and by using these parameters, the new equation has been obtained. Now what we have to do? We have to solve this equation, and the method of solving is the asymptotic solution. Asymptotic solution means it is close to the exact solution but it is not exact. So we shall investigate first the solution of this equation when y is very large, y tends to infinite. If y is very large, then value of lambda that can be neglected, because you see what is lambda. Lambda is equal to 2e by h cut omega. Now you are making y very large, y tends to infinite. So if you make y tends to infinite, and from the comparison of values of y and lambda, value of lambda can be neglected. So if you neglect the value here, that is if you make lambda is equal to 0 in equation 4.75, then this will become d square psi by dy square minus lambda square psi is equal to 0, because we have made lambda is equal to 0. So this is the new equation, and its asymptotic solutions are psi x is equal to e to the power plus minus y square by 2. I have already told the meaning of asymptotic solution, that means approximate solution. So if we put psi is equal to e to the power plus minus y square by 2, equation 4.76 can be satisfied. And you can check this, because you see this is psi. Next you calculate what is d psi by dy, and next you calculate what is d square psi by dy square, and you will see that d square psi by dy square is equal to y square plus 1 into e to the power plus minus y square by 2. You will observe it if you calculate. Now as y is very large, so that can be approximated y square into psi, because 1 can be neglected comparison to y, because y is very large. So d square psi by dy square will become y square into psi, that means equation 4.76. So if we assume the solution in this way, then this equation will be satisfied. But there is no logic behind the solution, that is why it is approximate, and we are saying that these solutions are asymptotic. Now out of the two asymptotic solutions, that is two solutions are obtained, one for positive value and another for negative value. C plus minus has been given here, but e to the power y square by 2 is not acceptable. Why? Because if y is infinity, then what will happen? That psi will diverge, because this is the expression for the psi. If we put y is equal to infinity here, then the value of psi will be infinity. That is not acceptable, because psi is bounded. So the exact solution of equation 4.75, that is the parent equation, that may be written as psi is equal to e to the power minus y square by 2. Why we are adding minus? Because from the minus sign, so what will happen at a particular point, suppose y is equal to infinity, value of this will be 0, so psi will not diverge. So the exact solution we are assuming, that is that may be written e to the power minus y square by 2 into hy, where hy is a function of y, hy is a function of y, and the product e to the power minus y square by 2 into hy tends to 0 as y tends to infinity, that I have already told. Because of the factor e to the power minus y square by 2, psi will be 0 for y tends to infinite, that is psi will not diverge. So after assuming the asymptotic solutions, we are now approaching close to the exact solution. So the structure of the exact solution should be like this. Now we will discuss about the details, that is how to get the exact solution, and we will proceed step by step. Now if we assume the solution like this, then equation 4.76 means if we substitute the value of y here, then what we will obtain? We will obtain if we put the value of psi in this equation, that is in this equation, then the equation will be like this: d square h by dy square minus 2y dh by dy plus lambda minus 1 into h is equal to 0. So after substitution of psi into this equation, we are having this equation, and this is known as harmonic equation. and we shall look for hy, a series solution of the type hy is equal to n equal to 0 to infinity an into yn. So how we will solve this harmonic equation? We will adopt a process that is series solution method, and I expect that you already have learned in your mathematical physics, that is how to perform the series solution method. So I expect you know the process of the series solution. So if this is hy, then what you have to find? At first you have to find dh by dy. Next you have to find d square h by dy square, and you have to substitute the values of h, dh by dy and d square h by dy square in equation 4.79 in this equation. And after the substitution and some simplification, you will obtain those steps we are not mentioning here, and I expect that you already know the series solution method. So if we substitute those values and after a little bit of simplification, you will obtain this expression, that is k equal to 0 to infinity k plus 1 k plus 2 a k plus 2 minus 2k plus 1 minus lambda ak into yk is equal to 0. So this expression we have obtained after the substitution and after some simplification process. Now for the validity of this equation, that means to hold this condition, the coefficient of each power of y must vanish separately, because y to the power k has been multiplied with this coefficient, and this should be true for all powers of y. So coefficient of each power of y must vanish separately. So if this coefficient is 0, that is coefficient of y to the power k is equal to 0, then from this condition, that is if we put the coefficient of y to the power k, that is the term in the third bracket, if we make it 0, so from that condition we can write a k plus 2 is equal to 2k plus 1 minus lambda divided by k plus 1 into k plus 2 into ak. This is the condition. This formula is known as the recurrence relation. Those who know about series solution, and I think they have must read about the recurrence relation. So I suggest you to go through some standard textbook regarding mathematical physics, and you see that how to perform the series solution method. So this type of relation is known as recurrence relation, and from this relation different a values can be found. For example, if you set k is equal to 0, suppose if you set k is equal to 0, then from the left side you will obtain a2 in terms of a0, and if we put suppose k is equal to 2, then a4 that can be found in terms of a2, but a2 can be found in terms of a0. So all even coefficients can be found in terms of the coefficient a0. Similarly, if we put k is equal to 1, then you will obtain a3 in terms of a1. Then if we put k is equal to 3 in the left side, then a5 can be expressed in terms of a3. But if you have already established, that is a3 can be expressed in terms of a1, then all odd coefficients can be expressed in terms of a1. So basically the fact is that all the coefficients that can be expressed either in terms of a0 or a1. That means all even coefficients can be expressed in terms of a0, and all the odd coefficients can be expressed in terms of a1. So equation 4.80, that means this equation, this 4.80 equation will have only odd coefficients if you somehow set a0 is equal to 0, and you will have only even coefficients if we somehow set a1 is equal to 0, as we are obtaining two different solution, that is in terms of a0 and in terms of a1, because I have already told that all even coefficients can be expressed in terms of a0 and all odd coefficients can be expressed in terms of a1. Now you look at the structure of hy. Hy can be expressed in terms of different a values, n equal to 0 to infinity, value of n is 0 to infinity. So you just separate the a values in two separate series, that is one for odd coefficients and another for even coefficients. Odd coefficients can be expressed in terms of a1 and even terms can be expressed in terms of a0. But if we somehow managed to set a0 is equal to 0, then what will happen? All even all even coefficients will vanish. And if we somehow manage to set a1 is equal to 0, then all odd coefficients will vanish. That is, in this way you can either vanish or all odd coefficients or all even coefficients. So basically the fact is that we have two independent solutions for equation 4.80. That is 4.80 we have two independent solutions, and the linear combination of the two will be the general solution. So we can express the solution in this manner. You see, we are writing HE. E means even, the subscript E means even. So we are expressing in this way: a0 plus a2 into y square plus a4 into y to the power 4 plus so on. Similarly, h0y or hoy, o means odd. So odd solution can be expressed in this way: y into a1 plus a3 into y square plus a5 into y4, in this fashion. So basically that is this expression, you have to use this expression for this purpose. So if we use this expression and if we calculate the different a values from this, you have to calculate different value of these coefficients from here. That is you have to find a0, a2, a4 in this way. Similarly, you have to find a1, a3, a5 in this way. So in that case, for odd coefficients has been expressed in this way by taking y common, because you see that is a1 into y, because from this expression the first term will be a0 into y to the power 0. Y to the power 0 means y only, so that is y to the power 0 means 1. So first term is a0, second term is y into a1, then a2 into y square, then a3 into y to the power 4, then a4 into y to the power 4, so a3 into y cube, then a4 into y to the power 4, then a5 into y to the power 5 in this way. But from the odd term we have taken y common. So after taking y common, we are writing in this fashion, that is a1 plus a3 y square plus a5 y to the power 4, in this manner. So these are the two solutions of the equation 4.80. Now just look that if we make k tends to infinity, in equation 4.82. So how to do that? If we make k tends to infinity, then 1 by k tends to 0. It is very clear. That is, if we make k tends to infinity, then 1 by k tends to 0. You just take common k from both numerator and denominator. So numerator is 2k plus 1 minus lambda, and denominator you just multiply these two factors. So this will be k square plus 3k plus 2. So from both numerator and denominator you take common, so k will cancel out, and in the remaining expression you have to keep in mind, that is 1 by k tends to 0, and you know how to calculate the problems regarding the limit. Several problems you have performed and you have learned in your higher secondary classes, so I think you can do that. So if we solve the problem by the concept of the limit, then you will see that ak plus 2 divided by ak, that is this expression, ak plus 2 divided by ak, that will be equal to 2 plus k. And just you have to consider the fact that is k tends to infinite. So if you solve in your notebook, you just write, then you will observe that ak plus 2 divided by ak is equal to 2 by k. Now another fact, suppose if you perform the Taylor series expansion of the function e to the power y square, then e to the power y square is equal to sum of 1 divided by k by 2 factorial to the power y to the power k, where k values are 0, 2, 4 in this way. So how we have done that? By applying Taylor series expansions. And I also expect that you know the Taylor series expansions process, which you have learned your mathematical physics. So e to the power y square can be expressed in this way. Now the ratio of the coefficients of two successive terms for the right hand side, suppose ak plus 2 by ak are two successive terms. So two successive terms can be expressed in this manner, that is, they should be k by 2 factorial divided by k plus 2 plus 1 factorial. So these are the, that is the ratio of the two successive terms. Now the fact is that, suppose from this ratio, if we simplify, then you just look at the denominator. So k by 2 plus 1 factorial. Now we know that 5 factorial is 5 into 4 factorial. 6 factorial is 6 into 5 factorial. And n plus 1 factorial means n plus 1 into n factorial. So we can do, that is k plus 2 plus 1, that we can take outside the factorial. So this will be k plus 2 plus 1 into k by 2 factorial, that is one term less. As I have told, that is 5 factorial means 5 into 4 factorial. So k by 2 plus 1 factorial means k by 2 plus 1 into k by 2 factorial. So in the denominator there is k by 2 factorial, and in the numerator also k by 2 factorial, though they will cancel out, and in the denominator only k by 2 plus 1 will be there. And if we that is assume that the value of k is very large, then this plus 1 factor can be neglected. So this will be only k by 2, and ultimately this will be 2 by k. So the ratio of the coefficients of the successive terms in this equation is given by this, and it is almost equal to 2 by k. And for equation 4.82 also, that in this series also the ratio a plus k by 2 and ak is equal to 2 by k. So what is the conclusion? The conclusion is that is age y, that function that we have assumed the form age y. So age y, that is expressed in equation 4.80, that age y actually behaves like e to the power y square. Why? Because we have already checked that if we express e to the power y square in Taylor series, then the ratio of the coefficients of the successive term is same as the function age y, which is expressed in this equation. So that is why we are saying that is age y is behaving like e to the power y square. Now we have assumed what is the nature of the solution, exact solution, that is psi is equal to e to the power minus y square by 2 into age y. We have assumed it before. Now if age y behaves like e to the power y square, then what will happen? If we put age y equal to e to the power y square, then psi will be e to the power minus y square by 2 into e to the power y square. That means it will be ultimately psi will be e to the power y square by 2, because e to the power minus y square by 2 into e to the power y square. And this is for even series. And for odd series, y will be multiplied with e to the power y square by 2. Why there will be multiplication? Because you see, for h0y, that is for odd series, y has been multiplied with these terms. That is why for odd series we have taken this factor extra, that is y into e to the power y square by 2. But whatever be the fact, the problem is that you see that in the expression of the wave function, and this expression, that is e to the power y square by 2, are there in both even or odd series. And there is the problem, actually these solutions cannot be accepted. Why? Because if you make y tends to infinity, then psi will be infinity, that is not acceptable. So this unrealistic solution can be avoided if the series in equation 4.80 terminates after a finite number of terms. So what we have said, you have to understand it clearly. You see that hy can be expressed like a series. So this is the series actually. And what is our assumed solution? Our assumed solution is like this, that is e to the power minus y square by 2 into hy. Now suppose we are able to terminate hy after certain terms, then what will be the fact? Because of this term only, that is as e to the power minus y square by 2 is there, so if we make y equal to infinity, then psi will be 0, psi will be bounded, then there is no problem. So our purpose is to terminate hy after certain terms. Otherwise, because if we take the solution in this way, that is in the previous processes, then psi is not acceptable. Because if we expand h in series, that is from this process we have learned that if we take the whole series, then the solution is containing the term e to the power y square by 2. That is not acceptable. So what we have to do, we have to take hy in such a way that the series terminates after some particular terms. If we manage to do that, then this particular term, that is e to the power minus y square by 2, because of this term, the value of the psi will not be infinity when we are making y equal to infinity. So what we have to do now, that is we have to terminate hy somehow. But how to terminate? We can terminate hy after certain terms if we look at the expression of the coefficient. This is the recurrence relation, and from this recurrence relation all the terms can be found out. So this recurrence relation is very important, because from this relation we can terminate hy after certain term. So how we can terminate? You see the numerator. The numerator is 2k plus 1 minus lambda, and suppose for a particular value k is equal to n, we have already said that is we are going to terminate hy after certain term. But after how many terms? We are assuming that is after k equal to n, that is when k equal to n, then this numerator will vanish. That is for the value k is equal to n, that means 2n plus 1 minus lambda is equal to 0 for k is equal to n. If we make the numerator 0, then what will happen? So after k is equal to n, this left hand side will be 0, that is we are not able to find the coefficients a after the value k is equal to n, then the series must terminate. So the series is terminating at the point k is equal to n. After that we are not able to find the successive a terms. So we are assuming the numerator vanishes at the point k is equal to n. So if we assume that the numerator vanishes at k is equal to n, then 2n plus 1 minus lambda is equal to 0. So we are writing 2n plus 1 minus, in place of lambda we are writing 2e by h cat omega, because we have already assumed lambda is equal to 2e by h cat omega in the beginning of our discussion. That is we defined two dimensionless variable. So there we have assumed lambda in this way, that is 2e by h cat omega. So 2n plus 1 minus lambda is equal to 0. So from this expression En is equal to n plus half into h cat omega. We are writing as En for different states. because n is equal to 0, 1, 2. For different quantum states, we are writing E and n is the subscript, and n denotes the different quantum states. So, value of the energy for the quantum harmonic oscillator should be like this, that is n plus half into h cut into omega. The energy value of an oscillator based on old quantum theory, this is from old quantum theory, is En is equal to n h cut omega, where n is equal to 0, 1, 2. But from the expression of En from the old quantum theory, we see a difference. From the two expressions, it is evident that the quantum mechanical energy value is higher than the old quantum theory value by half h cut omega. Because you see the expression, if we put n is equal to 0, then lowest value is half h cut omega here, but here n is 0, n is starting from 0, so lowest value is 0. So from the quantum mechanical expression, the lowest value is half h cut omega, it is not 0, but the spacing is h cut omega in both cases. The lowest value half h cut omega is a 0 point energy, and this 0 point energy is a manifestation of the uncertainty principle, because E is equal to 0 means that both position and momentum are well defined, and which is the violation of uncertainty principle. We have to understand this idea very clearly, because in old quantum theory E is equal to 0. If E becomes 0, then what will happen actually? If E equal to 0, then both position and momentum are 0 and they are well defined. But according to uncertainty principle, we cannot define simultaneously accurately both position and momentum. And we know the total energy E can be expressed in this way, that is p square by 2m plus half m omega square x square. Now you see that if the total energy is 0, and it is only possible if only both momentum p and x vanish simultaneously, because you see the expression when E will be 0, if both the first term and second term is 0. Now first term is 0 when momentum is 0, and the second term is 0 when x is equal to 0. So if both momentum and x vanish simultaneously, then what will happen? That means that position is also definite and certain, and momentum is also definite and certain, but this would violate the uncertainty principle, so this is not possible. So what we have deduced, that is lowest value E0 is equal to half h cut omega. So that is as per the statement of the uncertainty principle. And another important thing to note, that as we have said En is equal to n plus half into h cut omega, that is this expression En is equal to n plus half into h cut omega, where n is equal to 0, 1, 2. So from this expression we can also say that the eigenvalues are non-degenerate. Why? Because for each value of the quantum number n, there is a particular value of the eigenfunction and there is a particular value of the energy. That is why the eigenvalues are non-degenerate. We have already learned the fact about degeneracy and non-degeneracy. So from this expression, as the energy values are different for different states, as well as the energy, I will learn later, that is eigenfunctions are also different for different states. So we are saying that eigenvalues or the eigenfunctions are non-degenerate in nature. And if we plot the energy values in the potential energy diagram, then it will look like this. In the previous lecture, we have already discussed that the potential function can be expressed with a parabola. This line is a parabolic line. This line is the parabola, and it is representing the potential V is equal to half k x square. And in the same graph, we have drawn some horizontal lines, and these horizontal lines are representing the total energy values at different states. For example, this is the lowest possible energy. E0 is equal to half h cut omega at n equal to 0. This is the lowest possible energy and it is not 0. So this is a difference if we consider the either theory of the old quantum theory, that is there the lowest possible energy is 0, and in classical oscillator also the lowest possible energy is 0. But here in case of quantum mechanical oscillator, the lowest energy is not 0, the value is E0 is equal to half h cut omega, that has been shown in this plot. So it is as per the statement of the uncertainty principle. This is the energy for n is equal to 0, and this value is for state 1, n is equal to 1, n is equal to 2, and so on. So this is what about the energy values. I think you have already understood all the discussion. This discussion is from the book of Arul Das and H.K. Jain. So for further understanding, I will refer you to go through these textbooks very carefully. And I also thank you who have listened this lecture. And in the next lecture, we will discuss about the energy eigenfunctions. So thank you again for listening this lecture.